Okay, hi everyone. So I'm Artur Bergman. How many people have been here at the previous surge? So a fair amount. How many people have been here all 4 years? A couple. So I'm founder, CEO of Fastly. Used to be at Wikia, 6apart Live Journal. And I do run a CDN. So I'm going to try to avoid being too much of a vendor. So this is my 4th year here at Surge. Brian Control pointed this out earlier. And the talks I've given over the last year have been kind of the progression of Fastly, both from our original technology source, which was Wikia, onwards. And so I want to thank OmniTI and Theo and all the other team for making this happen. I'm happy to be here. So this is our origin. Many, many years ago, I took 2 servers, flew to London, and took a cab to Docklands and plugged them in. And that was beginning of 2008. And a lot of things have happened there. Now, the people over here last year and for the people who weren't here, I got into an argument with Tom Daly about Anycast, and he correctly told me I was wrong. So if you think I'm wrong, and Tom isn't here, but you also feel as strongly about it as Tom, please just call me at it or ask questions at any time. My statement is now that Anycast works if you know the guy who runs the fucking network that you Anycast over and you have something on him so you can call him at any time and tell him to fucking fix it. And it has to be a tier 1. If it's not a tier 1, it won't work. And you have to use the same tier 1 everywhere. So why are things slow? And it's usually because of latency, right? And what you really need to do is try really hard everywhere to avoid latency. There's 2 ways of doing that. One is just by avoiding it, and that one is by appearance of avoiding it. And quite often, appearance of avoiding it is just as good as avoiding it, though it does not always work. So latency is really annoying. It makes people bored. Right? We want things to happen immediately. So latency is a measure of time delay experienced in a system, the precise definition of which depends on the system and the time being measured. In communications, the lower limit of latency is determined by the medium being used for communications. Right? Or, as we know it, more waiting for shit to happen. Right? You see things spin, and you wait, and all the latency stacks up, all the little milliseconds and microseconds and nanoseconds, and then you suddenly have a really slow performing environment. So it obliterates your performance. But latency can be fixed, mostly, nearly always, except for certain fundamental laws of physics. And the key to this is dive as deep as you need to find the fucking source of latency and fix it. And it's easy to ignore. It's far too easy to ignore. Thankfully, at Fastly, we have Dormando, Alan Kassendorf, as the maintainer of Memcache. And if we ignore it, he gets really mad at us and tells us to fucking fix it. And then he forces us to do it. And it's a really good way of trying to not let latency build up. Because what happens is you have latency here, you have latency here, you have latency here, and you add it all together, and now it's really horrible. When I mean full-stack systems engineer, I really mean all the way down to assembly, not all the way up to Node.js. And latency exists everywhere, right? There's hard drives. Seriously, by the way, do people still use hard drives here? Why? Why? I don't get it. Moving a fucking arm around, that's latency. CPUs have latency. There's an awesome instruction that I've never figured out how to fully use because it's really hard. For matching strings in one in one cycle of execution. And it's a full crossbar, basically a regular expression on a 128-bit string. It takes 8 cycles to get the result, which is why it's really hard to use correctly. And it puts the result in another register. But that's latency. Human life has latency. I see it all the time, especially in California. AWS has horrible latency. This is actually latency measured as an aggregate of our customers against S3 from Ashburn. Ashburn is where S3 terminates. It's roughly, usually 0.8 milliseconds away from us, right? Like that's how far, if you ping S3, that's how far away they are. And the outlier here is nearly 4 fucking seconds of latency to get an object. But you can see others there, like, it's pretty horrid, right? So if you want to serve traffic directly out of S3, you should rethink that, especially if you're talking about many gigs per second. And I will give some credit that these are cache misses, right? So they are the coldest objects you can possibly imagine because it's objects we don't have. Still, 4 seconds to get a fucking object. I don't really know how you do that. And then networks, right? Fundamentally, networks are slow. And it's 75 milliseconds from this hotel to our pop in San Francisco. And that is because of that number. And that goes back to the physical law of speed of light. And in fiber, it's about 2/3 of that. So it's 124,000 miles per second. That sounds a lot. That's 25 milliseconds each way. Best case latency to San Francisco, as the crow flies, is 50 milliseconds. So the fact that you, from the shitty hotel Wi-Fi here, I get 75 is actually pretty impressive. And it's also not routed as the crow files. It probably goes from here to Atlanta, to Dallas, to Denver, to San Francisco, or Dallas, Las Vegas, LA, San Francisco. So that is a fundamental problem we have. And so there's this fallacies of distributed computing applies on the internet too. Right? Latency is not 0. And one of the fun things about working at Fastly is that we deal with the worst of distributed systems problem. Like, we have to write code that deals with unreliable networks that we do not control, run by assholes around the world who have political agendas. We have to deal with fiber cuts, some intentional, some not. And we have to deal with this ever-changing environment underneath us. The good thing is that we're a cache, which has this fantastic property that we LRU content after a while, so we can actually lose content without feeling bad about it. If we lose too much, we do feel really bad about it, but we only need to be transactional deletes, which lets us do some pretty interesting things when it comes to latency on the individual blocks. For example, if you have too much write pressure, you can actually throw data away. Or you can cache 300 gigs in memory because you can wait until off-peak to actually write to the disk. And but if we get a purge, we actually have to persist the purge, which warps your mind a little bit when you start thinking about it, but then you realize the code becomes much easier. And then our target time to first byte for cache hits is sub-millisecond and 99th percentile, which is a pretty strong target to hit, and we do it. So at Fastly, we have to deal with the fact that the network is not reliable, right? Like, we see split brain between our data centers pretty much, not continuously, but very, very often, right? Like, there's some fucking routing problem, or Netflix decides to fuck Comcast, or Comcast decides to fuck Netflix, or some way like that, and suddenly you have like insane spikes and packet loss, and now you need to find other ways to get to certain providers. So, and then Level 3 decides to reboot every core router they have in a 3-hour window with 30 minutes warning, and you're like, thank you so much. You just fucked the entire internet for half an hour. And we see all of that, right? It's fascinating to see it because we see so much traffic from so many websites. that individually you might not notice it, but we see so many packets and so much traffic from so many locations that you definitely do see it. And in this case, we actually saw it rolling from Frankfurt all the way to the West Coast because it did a rolling reboot. As I said, latency is not zero. The internet is fast, but bandwidth is not infinite. Even with 10 gig links, 40 gig links, 100 gig links coming, ISPs don't seem to want to provide them, probably because they don't have enough bandwidth, which is really annoying. So you always have to deal with bandwidth limitations. The network is definitely not secure. We have, friendly or unfriendly agencies within 100 miles that proves that. Topology changes all the time, right? People withdraw routes, people add routes. We had a situation where we were pushing about 5-6 gigabits per second to a large UK ISP. And we were doing it over Cogent. And we decided to move that traffic to level 3. So we move it to level 3. And 15 minutes later, they announced a more specific route over Cogent, therefore moving the traffic back to Cogent. Right? And you're like, fucking hell, there's another person at the other side deciding to traffic engineer me as I'm trying to traffic engineer him. Like, what the fuck do I do now? Right? And so it really is a continuous changing topology, and there is many administrators. And the network is very diverse. There are many vendors. Most of them suck. Most of them have bugs. All of them have bugs in different fashions. And some of them can crash a lot of routers, but there's a lot of gear out there. So a long time ago, the internet was really bad. The internet actually, despite what I just said, I think has become very, very solid. It relies on 5 buildings in the world to work. But apart from that, it is pretty solid. It is also lawless. And this is a map. It's not washed out. This is a map of ingress traffic to Fastly. And you can see there's what you're looking at is from the North Pole, and you can see there's a pretty strong graph between our Amsterdam POP and our San Jose POP, between San Jose and Ashburn. And then there is various requests coming in. And then this happens. And you look like it's a fucking ICBM attack from China. And it's all from China. We never get traffic from there. We suddenly get a metric fuck ton of traffic from there, which makes me want to block all of the country, close the firewall, and call it a day. And it was all SYN packets, non-spoofed SYN packets. About 95 gigabits per second of SYNs. 50% of it coming from China Unicom and China Telecom. 25% coming from AWS. Thank you, Amazon. And thank everyone who has a hacked fucking server on Amazon. Apparently, there's we saw, I think, 25,000 unique IPs on AWS sending SYNs to us. So that happens, and when that happens, you now have to go back and traffic engineer, find new routes, program your NICs to block. So the way we block DDoS partly is by programming the NICs to block traffic, programming the switches to block traffic, and then going up to IP tables. But at a certain point, you actually run out of 10 gig ports absorbing that amount of traffic. And your carrier is completely useless. So what happens is you call up the carrier and you go, hey, we're being DDoSed. And they go oh, we can null route one of your IPs. I'm like, how would that help? Well, all the traffic would go away. Yes, all our customers' traffic would go away. And they're like, yeah, but you wouldn't be DDoSed anymore. It's well, that's not really that helpful. So, yeah. How many here use active firewalls or stateful firewalls? Yeah, not that many. But congratulations, you now have a single point of choke for your DDoS. It will fall over instantly once you get DDoSed. And they also are usually massive latency sources. How many use stateful load balancers? Go on, there must be more people using F5s and A10s and other piece of shitty gear. Again, really single points of failure. I mean, you can have multiple of them. They're all going to fail because they're all going to see like 2 million different unique IPs hitting them, and they're all going to overflow their physical tables. They are going to move to CPU processing, and then you die. Basically, and even in best of cases, they add pretty unreasonable amount of latency. Comparatively to, a Trident 2 or Fulcrum Micro switch, which forwards packets in about 250 to 350 nanoseconds. So you basically want stateless load balancing all the way into your systems. Like, you don't want to keep track of any flow. You don't want basically, you never want anything that scales with the number of unique endpoints talking to you or the number of flows that are hitting you. So if you use sticky sessions, that is, I won't even say anything. And then there are people who go like, well, you can use OpenFlow. How many people here use OpenFlow? Wow, that's awesome. How many people know much about OpenFlow? So all of you other might run into people who want you to use OpenFlow. And so the idea of OpenFlow is that you have all these switches that have tables that you can program. And you have a central controller that programs these flows. And when you have an unknown flow, the switch stops the flow, asks the controller tells the switch where to send the traffic, and the traffic moves on. And this sounds really cool because you can now do really active traffic management across your diverse, non-chassis-based network. So first of all, it takes 9 milliseconds to lift that fucking new flow and ask for it in return. Second, you can only have one controller. So you have 200 switches, one controller. Yeah, that's really good. And then thirdly, all the controllers are written in Java, which has a stop-the-world garbage collector. So you're now your network controller, every now and then it's going to stop the world, and therefore stop all your networking. And you usually only have 4,000 flows. So if someone says, let's go down the OpenFlow route for load balancing, because that will allow us to use switches, just say no. Actually fire them. And then you have ELBs, which are a particularly hideous form of load balancer, where you give out an IP that belongs to one ELB. I believe that ELB is behind 1 gigabit port, which I'll go into later why that's wrong. And you cannot load shed effectively because you can't move the DNS entries. And they're really fucking slow. They're so incredibly slow that I can tell usually when, if I'm on a server in Ashburn and I'm accessing a customer's EC2 instances, I can tell usually if they're behind a ELB or not based on how fucking slow they are. And I believe they use an event-driven SSL server, which if you do and you have any form of actual request volume, will not work. Like, it just will not work. I think I went through it last year, but what happens is that, so the biggest CPU function on our server is calculating the square root for SSL handshakes. That's the single biggest CPU user on any of our servers. And so you're blocking doing that handshake. And on a very fast Xeon, which I'm sure the ELBs are not, and most load balancers are not, it takes about 600-700 microseconds of actual compute time to calculate a handshake for a 2K key. And so if your event server does that, it blocks all network traffic for that period of time. And if it does it a lot, you will see step functions of your SSL handshake time as latency increases. Now, admittedly, our solution might not be the most elegant, but we run Apache with 96,000 threads, and we can do about 40,000, 50,000 SSL requests per second, and about 6,000, 7,000 handshakes per second. And that actually scales. The latency stays pretty flat until you run out of CPU, and then it all goes to hell. But you get way, way more performance. So in general, like, our servers actually have probably about 200,000 threads running at any given time. And it turns out that the Linux 01 scheduler is really, really good. So a long time ago, our POPs looked like this. And I'm going to kind of walk through how we evolved the POPs. We had 2 machines. This is back in Wiki days. We plugged our ISPs directly in, and we used our link IPs. We realized that link IPs are not routed optimally because no one gives a fuck, so we moved to our own IP space. We ran BGP. We could go up to about 20 gigabits per second out of 2 machines, 50,000 RPS, and then we needed to add a 3rd machine, and we're like, well, now we need a ton more ports, and this is really annoying. So we put an Arista switch in front and used keep alive D to move traffic around and ECMP to low bounds, which is stateless. And we realized 2 machines was too fragile, plus keep alive D is a piece of shit, and VRP doesn't work. No one's disagreeing, good. So we moved to 3 machines per POP. We can now go up to 40 gigs per second, 75K RPS, and things work much better. So then we're like, OK, what if we want to go even bigger? This isn't very big, but. So well, actually, we weren't using ECMP here, but we moved to ECMP, and we moved to BGP on the switch. We reflect the BGP down to our machines, so we have the full BGP table. And the environment got much more stable. So then we decided we wanted to go much bigger. So we decided to build, we called them Super POP at the times. They were 3 different racks in 3 different Equinix buildings with fiber loop around them, switches, multiple switches in each rack, and each ISP coming into each rack. And for each machine, there would be no oversubscription to the internet. So like, for each machine that had a 10 gig port, there would be 10 gig coming out to the internet. And this sounded really good, right? This is the design, kind of what it was. There is a really big flaw here. It doesn't fucking work. And it doesn't work for a couple of reasons. One is because of spanning tree. And for certain reasons on the load balancing side, we need a layer 2 network. So it doesn't work because of spanning trees. You only get 2 paths instead of 3 paths. So we tried VXLAN over a layer 3 network. When I enabled VXLAN, LLDP stopped working, MAC address discovery stopped working, routing stopped working, and ACL stopped working. And I was like, OK, I need to disable this because the switch is not working anymore. So I hope VXLAN will be cool sometime in the future, but it's not there yet. But the biggest problem is, if you have a fiber cut on one of your 80 gigs outbounds, guess what? Those 220s can't handle the traffic, right? Like, you were used to pushing 80, and you now have at best 40, but most likely 20 because of spanning tree. So you very quickly run into this east-west bandwidth problem. So east-west is between machines, between racks, and north-south is internet and back. And we mostly care about north-south, right? We don't actually have much traffic between our machines. And then we went and designed a POP where we relied completely on east-west bandwidth for no actual good reason. And if you want to have no oversubscription, what you actually end up doing is for each port you get from a machine, and this is, you end up with 1 port to the internet and 1 port to the other switch and a 4th port to the 3rd switch. So you now use 4 ports for every machine, which rapidly uses up 10 gig ports. And if you're paying Equinix per cross-connect, it becomes very painful. So some people go like, hey, you can QoS traffic. And QoS works great if you have like a spike for about a millisecond. Same as buffering. If you actually continuously push 8 gigs on a link and you start QoSing or buffering, like, it's never going to catch up. There's like no time in the future where there's actually more bandwidth available. So QoS doesn't work. And then you can get really bad split brain problems. The only thing where I've seen QoS work well is if you have a control plane software and you want to make sure that that always goes through, and you QoS up SSH and control plane. Or you can do what my ISP at home does, which is QoS down everything that's not port 80 and port 443. So I can use GitHub on the web, and I try to check something out over SSH, and it doesn't work. I can stream 5 1080p streams, 200 meg down, at the same time, and I cannot keep an SSH connection open. It is fascinating. So we're building out our Gen 5 POPs. And we decided to stretch the definition of what a commodity machine is. So the 2690s V2s, the Ivy bridge-based servers, kind of awesome, 10 cores, 20 cores in the machine. The L3 cache size is insane. The 2 NICs. The 768 gigs of RAM is kind of mind-blowing to me. It creates a whole set of problems where you can no longer scan all of your memory to do things, because scanning the memory actually takes real time. So again, any kind of stop-the-world GC language will have severe problems with a 600 gig heap. Or, doesn't work. So yeah, one of the rules at Fastly is that basically GC languages are not, or runtimes are not allowed on the cache servers. At peak, I've seen cache servers do about 700,000 page faults per second. And so if you fuck with the memory on that machine too much, you get pretty bad stalls. And then we're putting in 18 terabytes of SSDs per machine. The main problem here is, for us right now, is actually getting SSDs. People are buying too many of them, so I kind of regret giving my talk 3 years ago. And we've even resorted to Newegg has 150 of them. Let's buy overnight, ship them to the office, and then sit and screw 150 SSDs in. Thank you, Jason. So our new rack design puts 16 of these machines in a rack and 4 64 gig port switches. And the idea is that we have no oversubscription on the traffic between machines and upstream. And the way we do it, so the switches are actually not linked together. If you ever stack switches, what you do is you take 2 failure domains and you turn it into 1 failure domain. And you take 2 individual backplanes and limit it by the fairly limited stacking backplane. So they're independent, and then we actually use basically ECMP multipathing instead of the bonding driver. Because we have 4 10 gig ports in a switch, in a machine. Each card has 64 IRQs, and you can bind those IRQs to different CPUs. Therefore, Intel does this pretty cool thing where they pre-fill the L2 cache with a packet and then interrupt the CPU to go look at a packet. And then you put this fantastic bonding driver in front of it, which is single-threaded, single queue, takes all your fucking ports, IRQs, and funnels it through one form. And performance dies. And there's also something called a team driver. Has anyone tried it? So I tried to try it, and the toolset for it only compiles on Fedora Core 15. And despite that, it made it into the kernel. And so I don't know if it works because I can't even compile it on any other Linux machine. So the performance, the performance per machine is about 2 billion objects. Each machine can push about 25 gigabits per second and do about 40,000 requests per second pretty easily. That was double. So one of those racks has 12 TB of RAM and 288 TB of SSDs. Cache about 16 billion objects and has 640 gigabits per second of possibly provisioned bandwidth. So the reason why we went to 768 gigs of RAM is that even at 12 TB of RAM to 288 TB of SSD, the ratio of RAM to storage is actually pretty freaking low. You have a 5% cache ability on your underlying storage. And so if we only had 384 gigs of RAM and only, we would have had 2.5% of RAM to storage, which made me feel a little bit uncomfortable. And the key here is, you have to use SSDs really well. So then we can take 2 of these racks together and get 24.5 TB next to each other and 128 10 gig ports for a total of 1.2 terabits. And what this does is that it completely eliminates the east-west bandwidth problem, because the switches themselves have terabit backplanes, and all communication between servers will go to the switch and back to the server. And all communication to the internet will go to the to the switch and then out to the internet. So there's no east-west links. There's no links between the switches that actually have to carry production traffic. So you have uncongested paths on all these links. And inside networks, this becomes really important as well when you start building out clusters that have to talk a lot with each other, because east-west bandwidth is a difficult problem. And so how many people here use spine networking? I love you, Mark. So spine networking is you don't buy a chassis. Chassis is a fantastic way of taking many, many switches and turning them into one failure domain. And even if you have multiple fucking control planes in it, they will all fail at the same time. So I've spent far too much money on Cisco and Juniper in my life, and I'd never want to buy a fucking chassis again. So spine networking is actually really cool and helps a lot reducing latency. So what you do is you have a spine of very, very fast 1U or 2U switches, and then each of your edge switches are basically plugged in with multiple links to all the spines. And then the spines, so if you have 32, you can imagine you have 32 ports coming in, and then you have 32 40 gigs up to a 40 gig switch. But actually what you have is you have 8 40 gigs links to 8 different switches. And now you can put 32 different sets of these on one, and you have uncongested full 10 gig bandwidth between any 2 machines. And so for us, what that means is we can put 4 of these together and get 4 terabits of capacity, which would be, a couple of billion sins a second if I decided to hit back on the fucking sin flood attacks. And trust me, I feel like, if we have all this bandwidth, we can just wipe them. And no, that would be bad. And so, what we do at Fastly is we also build private CDNs. So if you feel that you want to have one of these, or a couple of these spread around the world, you can talk to us, and we'll build it for you, and you can now have your own Akamai-sized network. Because their network is not that big. It's just a lot of shitty servers. Lots and lots of shitty servers. And it turns out if you have lots and lots of shitty servers, the latency adds up. So good ways of reducing latency is to cache at the edge. And traditionally, you haven't been able to cache at the edge because you can't purge, or you can't do the rule set that you need. We support Varnish, so you can do that, and you can purge instantly. And we have this thing called surrogate keys that let you cache and validate. So surrogate keys are actually really cool. They allow you to tag HTTP objects as you send them back to us. And then it allows you to purge on that object. And it takes about 150 milliseconds for the purge, 120 to get to all our servers. And then we can purge about 2 million objects per second. So a typical use case of this is you mark the objects with the object IDs as you send them to us, and the object ID changes, and you purge any object that referenced that. And it makes your life much, much simpler, and I wish I had had it 4 or 5 years ago. The other thing is, don't be afraid of assembly. It is awesome. So we had this problem that we needed to solve, so we wrote a bit of assembly. Actually, we wrote a Ruby script that generates assembly. So, you put the assembly in there, and then you put it inside a Varnish C block, and then you compile it and load it as a shared library. And we used to spend 25% of our CPU on virtual host matching, and now we spend basically 0% of our CPU on virtual host matching. And in fact, my laptop, my new laptop can probably do more like 400 million virtual host matches per second. And the nice thing about shared libraries is when you're done, you just get rid of them, and you don't have the malloc or free or anything like that. So assembly is awesome, even if I don't want to touch it myself too much. So we have several machine-based customers, or customers that have a lot of machine-based users. And apparently, people don't know what splay means, and everyone has cron jobs firing at the same fucking time. And unfortunately, NTP seems to be fairly accurate. So, we're really proud to host raw.github.com. We cache that at the edge. And they have insane spikes. And what happens is that someone starts a fucking Hadoop cluster or configures up 10,000 EC2 machines that all fetch their config at the same time. And like, you go from, I'm not going to give the exact numbers, but let's say you were at 10 bytes per second before, and you're suddenly at 400 bytes per second for 2 seconds, and then it goes away. And hit rate goes from a certain percentage to 100% for about 2 seconds, and then drops back again. And so what this does, I hope at least, Mark might disagree, but is that it offloads origin. So origin, sees one request. We love you. And no matter how many idiots are firing their cron jobs at the same time. We also did, so we do, for anyone who's involved in an open source project, we'll host open source projects for free. So we do Python.org and RubyLang, and sometimes Debian puts their security stuff on us. And oh my God, there are lots of Debian machines that do apt-get update on the hour, every fucking hour. It is amazing to see that spike. One key here is that even if you only run like a 5-second TTL, you will pretty much completely offload origin. And it's another example of where a 5-minute chart or a 1-minute chart will not help you identify what's going on, because it literally lasts for 1 to 2 seconds, and then it's over. And the reason why it only lasts seconds is because we run a pure 10 gig network. And the way you handle this, because there's only one way of handling it, is by having a metric fuck ton of 10 gig links. And then we do something called origin shielding, which is that we only fetch once from origin. And it works pretty well, right? You fetch the object, it gets put into L-free cache, and you blast it out to all the clients, and they hopefully go away. And if you actually saturate some port, that's actually where buffering might help you, right? Like the extreme spike that lasts for a second or two. This works great for like iPhone live streaming as well. So a lot of people seem to still deploy 1 gig networks, which is unbelievable to me. Like 10 gig is actually not that expensive, and it solves so many of your life's problems, specifically waking up in the middle of the night because the network is fucked, which I'm sick and tired of. So if you're pushing a 1 meg file, right, and you have 100 users, and you just get another 20, you're fucked, because you're now at gig, you're now at capacity. If you have 25 gigs and you add another 200 users, who the fuck cares, right? Like you have that capacity, so you don't need to load shed instantly. And this is where the ELB thing with the IP numbers that get tied to a user to an ALB, like you can't load shed quickly. Like you have to wait for the TTL to expire, and then you have to give it a new IP. So if you happen to give that IP to a few too many users, you're not saturating 1 gig links. And again, QS doesn't work. So if you're building a network, go for 10 gig. If you feel like spending the money on AWS, get the 10 gig machines and just like abandon 1 gig. It's not worth it anymore. That said, if you're pushing 25 gigabits per second, you need a giant amount of RAM for the retransmission buffer, and it's all higher order allocations. So if you have a network blip, you suddenly need like a couple of gigs of RAM in the kernel to keep your retransmissions. And that can cause some pretty interesting bugs to occur. So we had this kernel panic problem where we were on 2.6.38. We migrated to 3.66 with a set of IP metric networking statistics gathering patches. And it wouldn't crash very often, but every now and then it would crash. So Dormando going like, fuck this, we can't have shit crashing, we need to fix it, went and removed the patch and put it on a production machine, and it crashed within 24 hours. We're like, so our patch made the original bug not happen as often. That is strange. So the good thing is we have a lot of servers around the world, so we started running a matrix of different kernels between 3.2 and 3.6 and then 3.7, and we could not fucking figure out what caused them to crash. Like, they all crashed. Except when we started looking at the geographical distribution, you'll go like, why does Chicago never crash, but Amsterdam fucking dies in 8 hours, right? And like they push similar amounts of traffic. What's going on? And so it turns out that Chicago has a very, very small geographic catchment area. So the retransmission rate is significantly less than Amsterdam, that has all of Africa and Russia. Like, I think retransmissions in Amsterdam are probably like 1.5%, and in Chicago it's like 0.3%. And so it turns out there was a ref count leak in the retransmission timer in Linux that existed between 3.2 and 3.8 when we got it fixed, or we helped them give them enough data to fix it, because of this geographic diversity. And that makes some bugs really hard to track down. So I'm going to leave you with one useful slide, which is change these settings and change them now, or on the init CVND, upgrade to a new kernel, which has it by default. So the SYN backlog is how many SYNs will be outstanding. It's set to 1024 to conserve memory. It conserves 64 bytes per entry. So I'm pretty sure we can afford to have 65,000 of them. If you go higher, the kernel will silently truncate the value to unsigned int 16 and put it at 0. So don't do that. I did that by mistake because I was tired, and I put in 65536, and did not understand why we like dropped accepts like crazy until I read the kernel source. Congestion window, really important to increase it. Google's been arguing for it for years. It makes most pages about 20–30% faster if they're large. So I just do it, and if you don't want to do a new kernel, you can just add it to the route, to the per route setting. And then slow start after idle should be set to 0. Most definitely be set to 0. So what it means is that after 2 seconds, Linux goes into slow start again. And you get penalized all the way down to like a couple of packets, and then it goes up and up and up and up and up. And so if you set this to 0, it will remember what the window size is and just push data down. And if you know that you have like gig network or 10 gig network or a good origin, if, you set that and performance increases. It really helps the keep alives to work better. And as far as I can tell, I haven't seen any downsides. So the other problem that we run into a lot is MTU problems. So people like encapsulating TCP packets, well, IP packets in MPLS and GRE and whatever fucking format the cell phones use, when it's like GSM, GRE, or some shit like that. So if you're roaming, like let's say you go to Brazil with an AT&T phone, you're actually going to be routed back over a tunnel to Amsterdam, where you're going to be exchanged over a specific GSM exchange, and then be tunneled back probably to Chicago or New York, where you're going to exit to the internet. And you're tunneled so many times that your MTU is probably down to like 1100. And if you don't do MTU clamping, this kind of fucks things up. So we had an MTU problem in the UK where Vodafone and iPhones would not work over SSL. And it turns out that they do massive carrier-grade NAT. So if you're from the UK and you use Vodafone, all of you look like you come from 1024 IP numbers, right? Like, it's a 1/22, and that is all Vodafone UK. It might actually be all Vodafone fucking Europe, but I haven't confirmed that. So port 80, those fuckers proxy, like HTTP proxy. So they terminate it, and they reopen the connection, and that's why it works. For free, they actually just NAT it, but they don't do the MTU clamping correctly, so they send a much too high MTU. And so I think Google, when they did Android, just forced the MTU down to like 1150 if you're on the cell phone network to get around this problem. And iPhone still advertised like 1440. And so you don't clamp, you get IP fragmentation, which usually works, except if you have a shitty fucking carrier-grade NAT system that drops fragmented IP packets and doesn't send back any ICMP saying they've been fragmented. So it would take a cool like 45 seconds to exchange 5 packets with a cell phone. And actually, I couldn't debug it until I went to the UK. The cool thing here is because we pull BGP down to each server, and you can set these settings per route, and we have 460,000 routes, we did this. If Vodafone exists in the BGP path, set the fucking kernel MTU to 1,000 and the MSS to 940 and call it a day. And if we didn't have the routes, we would have to like slash the MTU for everyone, which would be horrible. But now we're just telling Vodafone to go fuck themselves. So it's a quick tour of, I have no idea how I'm doing on time, but quick tour of things we've been doing at Fastly over the last year. So if anyone has questions or corrections, I would love them. Well, last year there were some. Are going to be worse than last year?
How many F-bombs do you think you dropped from that time?
Say again?
How many F-bombs do you think you dropped?
I have no idea. Like 35? 25? I don't know. 42? Awesome. Allspo.
Initial congestion window, is it useless or neutral when talking about internal machines talking to each other? Isn't the max initial congestion window cached?
No, not the initial. The max window size that quickly can get there is kind of cached. On an internal network, I would just set it to like 100 to just get the fucking packets flowing as soon as possible. It won't matter that much because you're microseconds away, but there's no harm to it really, unless your network is really congested, but then you have other problems. So yeah, I would just increase it. I've been testing. Well, Microsoft for a while ran it. They set the initial congestion window to the advertised window size of the client. So if your first request had a window size of 64 packets, they sent 64 packets in one go down to you. I think they stopped doing that, but it made their websites faster for clients with good bandwidth. So, yes, Mark?
What's next in version 6?
Of the POPs?
Yeah.
I don't really know. More RAM? I don't know.
What's the problem in version 5?
We haven't really ran into problems with version 5 yet. I'm sure we will, but we haven't yet. And I will report on it next year. We'll probably be on version 8. Yes? So we monitor that on Aristas, and when we get DDoS, we saw a little bit of it, but not generally, because we don't have any oversubscription generally, so we don't really see it. Where I've seen it before is when you have to downgrade 10 gig to a bunch of 1 gig ports. Say again? Your machines in the new designs not talk to each other? No, they do talk, but they talk fairly little. But that's mostly like we try not to run the pipes hotter than like 7 gigs per second. So there is absorption area there. And then also, have you played with the RTO at all? Jason, have we? The RTO? We have not messed with it, apparently. Any other questions?
Yeah. Anything you're expecting to have to change with HTTP 2.0?
Yes. What it is, I don't know. I mean, I think it's a flawed thing to put flow control at that level in the stack. I understand why it has to be done, because the underlying protocols. I mean, if we had SCTP, yeah, then I mean, that would deal with a lot of these problems. But there are cool things we can do with HTTP 2.0 with the server push mechanism, predictive stuff, and so on. So I'm looking forward to that, and hopefully trying to figure out like how we can make things faster that way. But I'm sure we'll have to write a lot of interesting code to do with the flow control stuff. Yeah. Yes, that's why speed is really annoying because it requires SSL. And actually, the biggest problem with SSL is cert management. Right? So if you signed up for us and you want a cert, we have to go to our cert provider, and they will send an email to your domain name registrar like email that you have registered. How many people here know how to check that? Right? Like any large organization will take roughly 2 weeks to figure out who has access to read that email account, and then you need to track them down and force them to read an email account that's generally full of shit. And it's really, really annoying. So I think that's the biggest annoyance with SSL, the search. It would be better if we had SNI, but I hope we can go to SNI very, very soon. Yeah?
Have you seen any issues with 24 gigabit certs?
I mean, they use 4 times more CPU. That's it. If I'd been smart, I would have bought a 10-year 1024 cert the day before you weren't allowed to sell them anymore, and then tell the world that I enabled SSL and didn't see any more CPU usage. But yeah, no, it's just more CPU. Yep.
On VXLAN, did you get those issues with console? Did you compare? Are you going to get back to VXLAN? Do you think those are issues or architectural, or just because the software stack doesn't want it?
Yeah, I'm sure it's just like it just needs maturing more. I actually kind of like certain aspects of VXLAN. I don't like the multicast PIM stuff. I think it's just immature. It just needs more testing and more interop. So VXLAN is for people who don't know, VXLAN is a way to bridge layer 2 networks over layer 3 networks based on a combination of multicast, UDP, and tunnels, and VLAN tag, like VNI tags that go up to 16 million. I mean, ideally, I would love the world to just run layer 3 networks, but there are some use cases. Any more questions? Yeah.
I'm curious because we saw some attacks similar to yours. Did sync cookies help mitigate that, or was it purely?
So it turns out sync cookies, like our Xeons, run out of CPU calculating SHA-256s at about 2.5 million SYNs per second. And then you're pegged. So they help. Sync cookies help a lot with stupid attackers. And there is a lot of stupid attackers out there who will send you like 10,000, 50,000 SYNs a second and think they're doing damage. They're not as stupid as the people who like fetch a cache page 100,000 times a second and think they're doing damage. But they're pretty stupid. And then they help there. But at a certain point, you just overwhelm the CPU. Yeah, well, at a certain point, we started having bandwidth issues, but that was several 10 gigs more of traffic. The CPUs run out of sync cookie capacity too early. I've been wondering if we just patched it to use CRC32, we could go up to 14 million SYNs a second. Seems plausible, but I haven't had time to look into that. Yeah, I guess no more questions. So thank you, guys.